All right, so now let's talk about energy a little bit. And so I already told you how to calculate rotational kinetic energy, but let's spend a minute here and look at it a little bit closer. So you may remember from our first definition of kinetic energy that we used 1/2 mv squared. So you can reuse the fact that, okay, so we found a way to calculate v or related to angular speed, so we could use it in here, and then seeing that for a point that is rotating around this axis here, this is actually the rotational inertia, we can find this equation for the definition of our rotational kinetic energy. Another way to do this, and we talked about that a little bit before, is if we start with 1/2 mv squared and we draw the analogy, so we're going to have 1/2 m is for inertia in linear motion. So here we're going to be using I instead, and for v we're going to replace the v by omega r angular acceleration. This is incredibly slow. Okay. All right, and we end up with the same result. So this is derived from a point going into a circle, but generally you can use this for any object that has a rotational inertia I and an angular speed omega. And so in a lot of ways you can use this the same way that we used kinetic energy in the linear case. And so one example is to look at, an object that is going down a ramp, and you could look at, what is the initial height, and if we start from 0, how much kinetic energy is going to pick up, how is um, given how it's traveling downward. But so it still holds the same idea. It still gives you the amount of energy for an object that is moving, but this time it is an object that is um, going through rotational motion instead. So you could be measuring the rotational kinetic energy of your bicycle wheel, for example, or you could also measure that for here an object that is going through circular motion. Okay. All right. So next we're going to talk about momentum and how we're going to address momentum here in this new context of rotations. So stay tuned. Thanks. Bye.